So hello everyone and welcome to this next lecture in the DC to DC converter lecture series. And in this lecture series now we are covering the SEPIC converter. So in the past week we had done some basic analysis on the SEPIC converter waveforms. We had run the simulation at a constant duty ratio of 0.3 and we had looked at, most importantly, the inductor current waveforms. So we had tried to then compare the inductor current waveforms with what we might expect from the operation of the circuit. So in this lecture, let's continue. So as before we start the lecture, a quick background that if you are interested in these kind of video lecture series, but you want something a little more comprehensive as an entire online course, I do have an online course on the MOOC website Udemy, and this is on simulating power electronic circuits using Python. In this case, I go through the entire process. I talk about how you can install the software, some basic theory, and a complete case study on simulating a buck converter. And if you would like something a little more on the control side or digital signal processing side, I have another course on basics of digital signal processing for power engineers. And in this, I talk about how you can design a filter in the digital domain and implement it using Python. So I talk about some basic theory of signal processing. I also go through an entire case study in which we simulate, or rather we design using frequency analysis, response analysis, a low pass filter and a band pass filter. So anyway, these are a few courses which I have. If you are interested in doing courses online but you want something more comprehensive than just this weekly lecture series that I'm currently doing. So anyway, with this I'll come back to my lecture. So let's go back to the file browser, and this is where we had stopped off. So we had seen that there are two currents, that is the inductor current I1 and I2. Let's go back to my circuit. So this is the current through inductor L1, that's current I1, and this is the current through inductor L2, which is I2. And we had compared these two in this graph. Now, quite surprisingly, we had seen that current I2 is larger than current I1. Now, there is no absolutely reason for this, because as you can see, current through inductor L1 is the input and current through inductor L2 is at the output stage. Right? So you would expect the input greater than the output, but it's important to note that we are running this at a very low duty ratio. So this switch S1 is switched on for a very short period of time. Right? And it is during this short period of time the current through inductor L1 rises. This is when the inductor L1 is charged by the input voltage, and this inductor is also being charged but by the discharging capacitor. So you need to understand that the primary source in this case is this input voltage, and therefore it is this input voltage ability to charge the system that really impacts the level of the inductor. Now, to verify this, let's go over to our editor. Actually, let me close down this graph because we can now look at another graph. Actually, let me go back to my editor here. Now, the modulation signal is at 0.3. Now, I'm going to change this to, let's say, 0.6. Right? And let's run this simulation again. So we run the simulation, and of course, we can just go and have a look at the inductor current. Now, initially, this inductor current is going to have a lot of oscillations, but let's at least verify. The most important thing when we run a simulation is to check if there is any error in the console log. That's not there, so that's good to go. So as expected, there are oscillations, but as you can see from this envelope, you will see that the current I1, the blue line, is larger than the orange line, which is I2, right? So this already gives us an indication that what we expect is what is happening. That now that we have a larger duty ratio, the current in inductor L1 is larger than the current in inductor L2. But anyway, let the system settle down and then we can zoom in a little. So let's simulate this. And it is still in the process of settling down. In the meantime, let's check out the other two voltages. That is the output voltage So the output voltage this time is much larger, right? So let's say, for example, let's zoom in between 15 and 20 and figure out where it is. So the Y zoom is 15, the lower limit, and 20, and you can plot it again. Alright, so with this we seem to have something around 17.3, right? Approximately. You can zoom in again. If you want, you can zoom in between 17 and 18. You will get a much more, at least a better approximation over the voltage, but this is good enough. So let's go over to our circuit simulator spreadsheet and let's do this calculation. So we have an input of 12 volts. We have chosen a duty ratio of 0.6. So that means our expected output is input voltage multiplied by duty ratio divided by 1 minus duty ratio. That is 1 minus 0.6. And this comes to be 18, right? So what we have here, well, I closed it down. What we have here is around 17.3, 17.4. And as I said, there is going to be some drop because we have parasitic resistances everywhere. We have parasitic resistance for all the inductors. We have a diode drop resistance, and we also have a parasitic resistance for the capacitor, right? So these will account for the drop that we see from the expected voltage. But what's important is we are achieving an output voltage which is greater than the input voltage. So this is working in boost mode, right? So anyway, let's just save it, make sure we didn't edit it again. Now we should have a better result. So let's go and plot it. Actually, I also wanted to plot the capacitor voltage. Let me just do that. So this is the capacitor voltage, and if you see, very interestingly, the capacitor voltage is still at around 12 volts, right? This is a very interesting result. Okay, see, we saw our output voltage has been boosted up to around 17.4, right? But our capacitor voltage has not changed, right? So the decoupling capacitor voltage still remains at this same level, right? And this is kind of supporting our theory, as opposed to in the case of a Chook converter. It's important to note that the placement of the inductor L2 was different. Let's go out to our circuit. You see, this was the position of inductor L2. L2 was here, which means that this capacitor and this inductor exchange energy in the series path, right? Here that's not the case. Here the capacitor is only discharging through this inductor, and similarly the capacitor is charged only when the switch is off and in the forward direction. So in this forward direction, when the switch is turned off, the voltage source charges the capacitor, and voltage source and the inductor charge the capacitor and the output voltage, right? So we have a series path. We have a series path where the voltage source, the inductor, the capacitor all appear in the same forward path. And therefore, in the boost mode as well, even though the output voltage is larger, because we are adding up the energy of the voltage source and the inductor, therefore the capacitor does not have to be a larger voltage. Capacitor still remains at the same voltage. So this is a decoupling effect of the capacitor, right? So the capacitor acts as a decoupler, but at the same time the voltage doesn't follow the output voltage, right? So you see the voltage stays close to the input voltage. Anyway, more on this later. Let's go check out our inductor currents. So this is the inductor currents. As you can see, now we can zoom in. So let's zoom in between 0.25 and 0.251. Actually, let's go and check out. I would also do a Y zoom at the same time. So our Y zoom can be between 1 and 4. Let me close this down. Go to the web browser, and the inductor current is 0.25, 0.251, and Y zoom is between 1 and 4. let's go back here and we see we have a better result. Okay, we could have zoomed in into 0.35, but I think this is clear enough. So here we see the current I1 is larger than this current I2, right? And that is quite obvious. As I said, the reason is simple. We are turning the switch on for a larger amount of time. The duty ratio is 0.6. Right? In the previous case, the duty ratio was 0.3, which means the duty ratio, the switch is turned on for 60% of the time of one switching cycle. Alright, and during this time the inductor is charging, so their current is flowing in the clockwise direction. So really speaking, this inductor current can rise to a large value, and that's what it has happening here, right? Because there is almost no other impedance in this path. There is no other inductor, no other capacitor. All these others are just parasitic resistances, right? So now when the switch is turned off, the inductor and the voltage source charge through the capacitor in the forward path, right? And remember, the inductor doesn't appear here. It is a complete forward path, voltage source, inductor, capacitor, diode, and then the output capacitor, right? So really speaking, the inductor doesn't appear anywhere here. The capacitor has a charge, but it's important to understand here that the voltage source and the inductor are charging the capacitor and the output capacitor, right? So therefore, this output capacitor ends up getting boosted, and that's the reason why the capacitor does not achieve a larger voltage. We saw the capacitor voltage is still stagnant at the same level. So that means that this current is expected to be much larger than what it was when we chose a smaller duty ratio. Right? When the switch is turned on, the capacitor charges this inductor in this clockwise direction, in this anti-clockwise direction. But it's important to understand here that this capacitor, alright, because its voltage, and that's probably the reason, we'll look into this a little more probably in the next lecture. When the switch is turned on, this capacitor discharges through the inductor. But it's important to understand here that the inductor is also providing a current to the capacitor when the switch is turned off. So when the switch is turned off, you have the forward path conducting, and at the same time the inductor is charging the capacitor, which means that most of the energy which it does acquire when the switch is turned on is then utilized in charging the inductor, right? This explains the reason why eventually it is this inductor L1 which forms the input stage and this inductor L2 that forms the output stage, right? So even though we are working in boost mode, the current in inductor L1 is larger than the current in inductor L2, and this kind of can be explained if you look at the circuit, right? So you just have to see where the energy is flowing, right? This definitely has more energy than this one, alright? So now with this, let's go back once and have a look at the capacitor voltage again. Now that we have a look at the capacitor voltage, let us also look at the current in the capacitor. So I do believe we measured it, that is ammeter C1. So let's add a plot. Capacitor current, we have it. Start plot. And ammeter C1, so we just give it IC, should be good enough. So let's just plot this and see what we get. So initially it's better just to plot the entire plot so that then we know where to zoom in. This is capacitor current. So the capacitor current, let's zoom in between, I would say the same amount, 0.25 to 0.251, but most importantly, let's put the Y zoom. The Y zoom can be minus, I would say, minus 4 to plus 4. So let's do that. Let's go back here. So 0.25, 0.251, minus 4 to 4. So this is the capacitor current, and yeah, this is what we get. So now let's take a look at what's going on here. So as we already know from the circuit, this capacitor is charged when the switch is turned off, right? So in our case, we are measuring the current in the right hand direction, right? The current is moving in we are measuring the current in the right hand direction. So in order to be able to check this out, let's plot it with respect to the inductor currents, right? Let's go back and create another plot. Inductor and capacitor, right? We already have it, very nice. So we can put IC, save the waveform, L1, I1, and the last inductor L2, which is I2. We are done, and let's just come here and plot. We already know, because -4 to 4, right? Because we're just using the capacitor current was larger, so there's no real need to plot this again. Okay, let me just stop the simulation. I think we have enough results. No, this is not the one we needed. Yeah, inductor and capacitor current. So let's come up here and check out what's happening. So if we have a look at what's happening, when the currents are rising, alright, when the currents are rising, the capacitor is rising, but in the negative direction, right? Now this is the reason why I wanted to plot it, right? Because now we can compare. So what this means is, if it is negative, right, let's go to the circuit. The current is flowing in this direction, right? If this current is negative, right, that means it is expecting a current that flows in the left. That's what it obviously means. That means we are expecting a current that flows to the left, right? That's the positive polarity of current with respect to this ammeter. Now let's come back here. Here we see that both inductor current but that is IL1 and IL2 are increasing, right? Okay, this, I just remember the color coding is different. I see the blue line is the capacitor current, the orange line is the current through inductor L1, the green line is the current through inductor L2. So now that we have this, we see here that at this point of time, the same current as the current through inductor I2 is now flowing through the capacitor. And that only makes sense. The reason is that when the switch is turned on, we have this path, right? That is, the capacitor is charging this inductor L2, right? And that's what it shows. This current here, if you look at the peak, it's -2. And if you look at the peak of the green line, that is current through inductor L2, that is also 2. It's just that the polarity is different, right? When the switch is turned off, right, that's when the current flows in the forward path. And when that happens, right, we see something very different, right? So what we see here is that in this case, the current, that is the current through inductor L1, right, this current is now the same as this ammeter current. And the reason is because now the forward path is working, alright? So this shows how the capacitor behaves. This shows that the capacitor appears in two different circuits. When the switch is turned on, it appears in the circuit with inductor L2. When the switch is turned off, it appears in the circuit with inductor L1. This is how it takes current, takes energy from one particular inductor, and in the other case, it transfers it to the other inductor. Right? This is the role of the decoupling capacitor. Right? It takes energy from one source, gives it to the other source. Right? The only thing is here, the capacitor does not directly link with the capacitor does not directly charge into the output, discharge into the output. In the case of the Chuk converter, the capacitor was discharging into the output, right? So with this, again, this lecture has gotten long enough, so at this point of time I will stop this lecture. What was important is that we analyzed how the inductor currents behave and how the capacitor current works with respect to the inductor current, right? So now in the next lecture we will do an open loop control of the SEPIC converter, and finally we'll do a cleanup of the code. So as before, if you have any doubts about what I did, feel free to comment on this video or write me an email or message me on social media, whichever is your preference, right? So thank you so much for watching, and I will see you in the next week where we will continue with this lecture series. Thank you so much and goodbye for now.